Thank you very much, Dries. Good afternoon, everyone. Welcome to this Flanders Make Tech at Lunch session. My name is Sydney Goossens from Flanders Make at VUB, and today I'll be talking about optical fiber sensors for asset monitoring. Optical fibers, you might have heard of them for the application for ultra-fast internet. An optical fiber is nothing else than a glass wire, an extremely thin glass wire, as you can see here, the size compared to my thumb. And like I said, you probably know them for ultra-fast internet applications. But today we're going to talk about using these optical fibers as sensors. Now, we like to make the comparison of an optical fiber sensor system with the human nervous system better. Like we can sense pain where and when we get hurt. We will use these optical fibers in assets, for example, airplanes, but as we will see today, that can be very different assets as well, for monitoring the location and the presence of damage. Now, why optical fiber sensors? Well, first of all, they are very thin. As you could see on the previous slide, they are about the size of a human hair, diameter of a human hair. They can be multiplexed, meaning that we can have several optical fiber sensors in one optical fiber. And because they are very thin and we can have several sensors in one fiber, that means they are also very light. They are made of glass most of the times, which means that they are corrosion resistant. They transfer light in the core inside the optical fiber, which means that there's no interactions with electromagnetic fields outside. So they are immune to electromagnetic crosstalk, and they can measure statically as well as dynamically. Now, there are two types of optical fiber sensors that I want to discuss with you today. If we have our optical fiber, as here depicted in blue, we're going to measure that or we're going to use that to measure the temperature profile, for example, along the length of the optical fiber. We can first of all do that with what we call a point sensor. A point sensor is, as the word says, a sensor at a point along the length of the optical fiber at a certain location that will give us the measurement, in this case temperature, can be strain, pressure, etc., at that location. Now, one big advantage of optical fiber sensors is that we can combine different point sensors into one fiber, and that's what we call then a quasi-distributed optical fiber sensor. And we can go one step further, and that is the second type of optical fiber sensor that I want to discuss today. And that's where we use the entire length of the fiber for measuring, for this case, for example, temperature, and that you can see the temperature profile as dashed line along the whole length of the optical fiber. And that's what we call fully distributed optical fiber sensing. Now, in this Tech at Lunch session, I want to discuss I have three topics prepared. First of all, I want to talk about these point sensors, more specifically the FBG sensors, how they work, and we'll discuss two case studies. Second of all, I want to discuss the fully distributed optical fiber sensors, more specifically optical time domain reflectometry, and there we will look at the how the whole length of the optical fiber is working as a sensor. And also there I have two case studies prepared. And lastly, I want to discuss specialty optical fiber sensors, more specifically microstructured optical fibers. And also there the operational principle and a case study will be elaborated on. So let's start at the beginning with the optical fiber point sensors. As I already explained or mentioned in the first slide, an optical fiber is typically used to transfer light as far as possible for telecommunication purposes. That's why a classic or a standard optical fiber looks like this. Inside, we have the core of the optical fiber. That's where the light is guided. And around that, we have the cladding. That's what confines the light into the core. Both parts are made of glass with a slightly different refractive index. If we inject the light ray into the core of the optical fiber on one side, it will stay reflected in that optical fiber until it emerges on the other side, which is exactly what we want for telecommunication purposes. Now, if we do that with white light or light of all colors, well, all those wavelengths, all those colors separately will be transmitted through the fiber and will also emerge on the other side of the optical fiber. What is now the first optical fiber sensor, which is called the fiber Bragg grating? Well, that's actually nothing else than a wavelength selective filter. The FBG, as it's abbreviated, is a refractive index modulation in the core of the optical fiber. So the refractive index is modulated with a specific period in the core of the optical fiber. And that FBG, well, what will that do? It will reflect one specific color of light or one specific wavelength of light. So everything that is reflected around that specific wavelength, that will be our sensor response. Everything else that is transmitted, so everything except in this case the green lights, well, that will simply pass through the FBG sensor. And like I already said, that's our reflection spectrum centered around what we call the Bragg wavelength, because it's that wavelength that satisfies the Bragg condition. Now, what's one big advantage of these type of sensors? We can create different FBGs with a slightly different period of refractive index modulation at different locations in the optical fiber, so they all reflect at their own individual color, and we can have a multiplexed quasi-distributed optical fiber sensor. Now, how does such a sensor work? So we have our FBG with our periodic refractive index modulation. What happens now if we apply a strain on the optical fiber at the location of the sensor? Well, you can see it in the animation here. The strain will induce an increase in that period. So the Bragg condition will change, meaning that the reflected wavelength or the reflected color will also change proportionally to the strain that is applied on that optical fiber. Likewise, when we apply a temperature difference to the optical fiber sensor, the properties of the sensor will change linearly, and the wavelength will also shift linearly with the applied temperature. So the main advantages here is that we have a very linear response to the applied measurement. And second of all, very important is also that it's a wavelength-based measurement, meaning that we are looking at the color of the sensor that is reflected, not that the intensity of the light. So changes in optical power or optical intensity are not important here, because we are looking at the measurement is encoded in our wavelength-based signal. So that's the operation of such an fiber Bragg rating in a nutshell, of course. But now I want to discuss the first case study with you, which is an ongoing Flanders Make project called SAFOS, where we are using optical fiber sensors to monitor gears and bearings. Now, the traditional problem is that there are space constraints. Here you see there is a bearing. Well, you don't see it because it's in the housing, meaning that it's very difficult to access the bearing directly with sensors. So typically, if you want to monitor that specific bearing, you have to install the sensors, like you see this accelerometer here, on the housing itself, and you cannot come much closer than that. What's the advantage here of an optical fiber sensor? We can install the fiber, as you can see here, directly on the side of the bearing. You see it's installed with an adhesive here, and we can have multiple sensors in that optical fiber to monitor the strain at different locations on that bearing. And that's exactly what we did in the first part of the project. So we instrumented a roller bearing with, or ball bearing better, with 5 FBG sensors equidistantly spread along the outer raceway of the bearing. And we measured the strain at these 5 locations. On the right, you see the strain signal. Here it's still in wavelength. So it's the wavelength shift, which is completely proportional to the strain signal in function of time. And you can see the periodic signal from the balls passing that FBG sensor. Now, we included a micro machine damage on some of the bearings at this location here, which had a size of about 500 microns. And that damage, every time a ball passes the damage, it will induce an additional impulse peak, and that's the peaks you can see here, on the signal of the strain. And that will allow us to use these sensors to detect the damage, and not only the presence of the damage, but also the location of the damage as soon as it occurs here on the bearing. Now, we looked at not just one frequency, or let's say not just one amplitude of the strain signal. We looked at the strain signal at the BPFO frequency. What's the BPFO frequency? That's the frequency of the balls passing this damage here. And we look not only at that frequency, but at all its higher harmonics. And that's what you can see on the right graph. We have the number of the higher harmonics and the amplitude of the strain signal at that higher harmonic. And you can see from the graph that for the damaged bearings, we can clearly see a higher, or generally a higher trend in the amplitude at the higher harmonics than for the healthy bearings. And it's by taking the sum of several of these higher harmonics that you can differentiate between a healthy bearing and a damaged bearing. Now, this is ongoing research, so I will not spoil too much at this point, but that's one of the case studies here I wanted to discuss. The second one is still an asset, but in this case, it's a larger asset. I want to talk here about large stiff structures such as bridges, for example. Now, as you might know, the physical properties, the mass, damping, stiffness of a structure will change if there is damage induced on the structure. Now, to measure these parameters, we can do that indirectly by measuring the modal properties of our structure. That can be the natural frequencies, but also the mode shapes. And as you can see on the example on the left of the Tokuhama Bridge here, and a well-known example of how it went wrong. If we can use sensors to detect this before or as soon as it starts happening, we can avoid, of course, situations like this. How are we going to do that? Well, first of all, we're going to look at the strains at different locations along the bridge. Now, that's an issue, not for the previous bridge, but for normal bridges. Usually those strain fields or those strain amplitudes are very low, are in the order of 1 microstrain or lower, because they are induced by ambient conditions. That can be weather conditions, but also traffic passing over the bridge. But of course, we don't want that bridge to move too much. So typically the local strain is at a very low level, which is difficult to measure even with optical fiber sensors. So for that reason, we developed an optical fiber amplifier, or a strain amplifier rather, which is an aluminium shape that looks exactly like this. And we install that shape to the bridge or to the structure at the location of the holes here, left and right. And when the bridge applies a strain to this transducer, the strain will mechanically be amplified at this location here, and that's where the optical fiber sensor will be installed. So whenever a strain is acting on the bridge, that strain will be transferred to the transducer, and that strain will be amplified 32 times to the optical fiber sensor. We tested these transducers in a real environment here. This was a high-speed train viaduct in Belgium, where we installed 20 of the transducers along one span of the viaduct, as you can see also on the images here. And then when an ambient condition vibrates the bridge, in this case that was a TGV passing over the high-speed line, the strain induced by those vibrations will be measured with the optical fiber sensors at the different locations on the bridge. And the results you can see on the graph here on the right. So here you can see that we were able to reconstruct not only the mode or not only the natural frequencies, but up to 6 of the mode shapes of that viaduct. And you can see on the y-axis that the amplitude is indeed on a sub-microstrain level, but due to the transducers, or thanks to the amplifying power of the transducers, we were able to reconstruct the mode shapes of the bridge. And it's this information that can be used, because that will change if anything occurs or if any damage occurs on the bridge, then these frequencies and mode shapes can possibly change. That's the second case study that I wanted to discuss based on the point sensors. And the next part of this presentation will discuss distributed optical fiber sensors, where we will use the entire length of the optical fiber as one long sensor. How does that work? Well, to explain that, I want to ask a question first, and that question is, why does the sky appear blue? And that is the case because of a phenomenon called scattering. So scattering occurs when you have particles in the medium where the light is propagating that are of the same size of the wavelength of the light. That light will interact with those particles and will be scattered. So If you look directly at the sun, well, I don't recommend it, but if you would do that, you will see most of the colors in the white light spectrum are present in that spectrum. But what will you see if you look in any other direction to the sky? You will see blue light because the particles in the atmosphere, they are scattering mostly the blue light of that spectrum coming from the sun. So if you look in any direction except for at the sun, you will see that blue light because it is scattered by the particles in the atmosphere. And that's exactly the principle that we will use here in distributed optical fiber sensing. If we again inject light into our optical fiber on one side, for telecommunication applications, we want that light to reach as far as possible and emerge on the other side of the optical fiber. However, there are also impurities in the glass that are there from the manufacturing of the glass that we call scatter centers, and that will scatter a tiny amount of light nevertheless. And that an even smaller amount of light will be scattered back to the source where we injected the light into the optical fiber. Now we can see this as an optical fiber, or we can use that at different locations along the length of the optical fiber, where every small part of the fiber will be reflecting a little bit of light, and that will be, in this case, our sensor signal. Now, how does that work? Well, if we inject a pulse of light into the optical fiber, we will look at the start of the optical fiber, which light is reflected back, is scattered back from the optical fiber, and we will measure that in function of time. And because we know the speed of light in glass, we can plot this in function of distance. So in this example here, you see the pulse of light going into the optical fiber while we measure the light that is being reflected back or being scattered back better, and then you get this signature scatter profile that is a key to this type of optical fiber, to this optical fiber. This is the scatter profile that is unique for this optical fiber. Now, if we apply a perturbation in strain or temperature somewhere along that optical fiber, that means that the backscatter profile at that location will also change. And because, again, we know the time that the speed of light in the optical fiber, we know at which distance something is happening on that optical fiber, so we can measure not only where, but also the amplitude of the strain or temperature that is acting at that location. So that, again, in a nutshell, is how distributed optical fiber sensing works. Now, I have two case studies prepared here today. The first one is an application of distributed optical fiber sensors on weld monitoring. And the application here was a monopile that holds a wind turbine on an offshore wind turbine farm. Here you have different forces acting on that monopile. You don't only have the wind acting on the wind turbine, but you also have the currents acting on the monopile. These monopiles, they're typically, structured that are welded together. So as you can see in the simulation here, that means there are very high stresses induced on those welds of the monopile, and that's exactly why the damage will occur also at these weld locations first. So we want to be able to monitor these weld locations to understand better what is happening there due to the stresses on the structure. For that, we set up the following experiment. There we had, we used a steel beam of 5 meters long and 27 centimeters in diameter. The beam was well together here in the middle, and it's exactly there that we installed an optical fiber sensor completely on over the circumference of the beam. Now, we used a distributed sensing technique, so that means that the optical fiber that was installed, it was 2.5 meters long. And we had measurement points every 2.6 millimeters. So that means we had a total of 950 sensors in a 2.5 meter span of the optical fiber that was wound around this beam. Imagine doing this with electrical strain gauges, installing 1,000 strain gauges over a distance of 2.5 meters. That would be a cabling nightmare. And you can do this with one, or you can solve that with one optical fiber. And we used a commercially available measurement device that allowed us to measure the strain here at a frequency of 250 hertz. Now we induced a crack on the inside of the well, so on the inside of the beam, and then we loaded the beam, so in fatigue loading, to include stresses here on this weld location. What you see on the following graph is now the strain along the circumference of the beam, so along the length of the optical fiber, but here plotted radially. And here at the location of the crack, on the right graph, you see the location of the crack. You can see that the strain there started growing while the fatigue loading was ongoing. Because the crack was actually growing, it was propagating from the inside of the cylinder until the outside of the cylinder, and that induced increasing strains on the optical fiber sensor. So we were able to not only detect the crack and the location of the crack, but also follow the severity of the crack and the crack growth with this distributed optical fiber sensor. A second example to show, just to show that we can also measure temperature with this type of sensor, is a measurement setup for a 5th generation low temperature thermal grid. There we had a pipe of a length of 3 meters where we included a distributed optical fiber inside, and water at different temperatures was propagating through that pipe while the temperature was measured at 550 sensors, in this case, spaced 5.2 millimeters apart. We used our commercially available interrogator measurement system, and you can see the results in the next graph. This was here obtained at 25 hertz. What you see here is you see the temperature from the start of the pipe until the end of the pipe. So you see when we increase the temperature, first of all, there's an inclination in the slope here, meaning that we can measure the flow rate. So we measure the next temperature of water passing through the pipe, so we can measure the flow rate of that water. And then the water, different temperatures of water were passed through the pipe with 5 degrees incremental temperature. And you can see in the graph nicely the increment in temperature up to 40 degrees and then down again to room temperature. So we were able to measure the temperature at different locations along this pipe, not only for the flow rate, but also for the temperature of the water passing through the thermal grid. That concludes this session, or this section rather, on distributed optical fiber sensors. And then I want to end the presentation with one short section on specialty optical fiber sensors, more specifically microstructured optical fiber sensors. What is a microstructured optical fiber? Well, as I explained a few slides ago, a classical typical telecommunication optical fiber has 2 parts. You have the core, in which the light is guided, and you have the cladding, which makes sure that the light is confined to the core. And yeah, typically around that you also have a coating, of course, to protect the optical fiber. Now, core and cladding are both made from silica glass, so the whole optical fiber is made from glass. What is now a microstructured optical fiber? There we don't use a core cladding or a typical core cladding structure as in glass. We will use a microstructure of air holes, as you can see here, a hexagonal microstructure of air holes. And those air holes, they run around the whole length of the optical fiber. So here you just see the cross section of the optical fiber, but the air holes, they run through the whole length of the optical fiber. What's an advantage here? Well, we can tweak these configurations as we want. So we can change the layout, we can change the pitch, we can change the diameter of different air holes. So we can really construct a microstructure for an application that we have envisioned. One reason reason to design this air hole structure is, of course, for optical properties. So to make sure that the light is still guided in the optical fiber, we still need a core structure. And so that's why you see no air hole typically in the middle. That's where the light is guided. But then the air holes around it, they can be chosen in an arbitrary way for whatever optical or mechanical purpose desired. And the microstructured optical fiber that I want to discuss today is the one that we call the butterfly optical or butterfly microstructured optical fiber. Why? Well, I think you can imagine a butterfly shape in the microstructure here. So these air holes that you can see in the cross section, those air holes propagate along the whole length of the optical fiber from the start until the end. Now, what's the reason for this microstructure? Well, first of all, the first reason is optical. Because we have two, or it's a very asymmetric air hole structure, meaning that the light guided in the core will also see these two very different directions of material properties, and it will maintain itself in two different polarization directions. So first of all, we have the turquoise polarization direction, which sees this side or sees these material properties in this direction. And second of all, we have the purple polarization direction, which sees the material properties in this direction. So that's the optical advantage of these designs. What is now the mechanical advantage? Well, we can design the mechanical properties of these microstructures. For example, for this fiber, we have no air holes in this direction, or almost none, which means that if we apply a stress to the fiber from the outside, this direction will apply that stress to the core of the optical fiber, meaning that this purple polarization direction, which is traveling in that direction, that will see the stress applied to the optical fiber, while the other side will isolate the stress propagating to the core. So the turquoise polarization direction will not see the stress applied to that optical fiber. If we inscribe a sensor now, an FBG, into this optical fiber, we don't have one wave now traveling to the fiber, we have two. So that means we don't get one Bragg peak, but we get two, one for both polarization modes. And if we apply an actual strain to the optical fiber or a temperature difference, just like the classical optical fiber, both peaks will see the same effect, both polarization modes will see the same effect, so both peaks will move to the left or the right simultaneously. However, if we apply a transverse force or a hydrostatic pressure to the optical fiber, well, the purple polarization mode will see a different effect than the turquoise polarization mode. So those both peaks will not move simultaneously, but they will move towards each other or away from each other. And that's how we can use these specialty optical fibers, not only for actual strain or temperature, but also for transverse forces or pressures. The case study that I want to very briefly discuss here is one where we embed the optical fiber sensors in a composite material. You have to imagine that the gray block here is a composite material. We have our optical fiber inside. Most optical fibers, or the standard ones, they will be sensitive to the axial strain in the purple direction, but by orienting or by including the microstructure better into the optical fiber, we can also be sensitive to the green direction, so the transverse strain, or by rotating the fiber 45 degrees, we can even be sensitive to shear strains in that composite material. And by including not one, but two optical fibers next to each other, so we have the left one here that will be sensitive in a transverse strain in this direction. We have the right one here that will be sensitive in a transverse strain in this direction. We can actually measure the strain in all three dimensions of space with these two optical fiber sensors at this location. And an application there is, for example, cure monitoring, where we use these sensors to monitor the manufacturing process of a composite material. And you can see here in green, for example, the temperature going through the different stages of the manufacturing process, something you could measure with a classic optical fiber as well. But what you see in blue here is the peak separation, so the distance between the peaks, which is proportional to the transverse strain. And that is something you could not have measured with a traditional optical fiber or any sensor actually, which measures here the consolidation phase, so you can clearly see the increase in transverse force at that location on the optical fiber. That's one example, but you can also use it for load monitoring or damage detection in composite materials, for example, in aerospace applications. And that concludes this Tech at Lunch session, where I want to first summarize some take-home messages. So for the point sensors there, we discussed the FBG sensors, which is a local wavelength filter. You can have up to 100 sensors per fiber, measure strain and temperature with a spatial resolution as small as 2 millimeters, and you can achieve very high measurement speeds there up to gigahertz. With the distributed optical fiber sensors there, we will use the whole length of the optical fiber, and you can have up to thousands of sensors per fiber. Again, measure strain and temperature with a spatial resolution in the millimeter range, and you can go up to hundreds of kilometers there, but then your resolution will also be increased. And then we also had a look at the microstructured optical fiber sensors. So they have great design flexibility for enhancing, on one side, the optical properties of the fiber, but also the mechanical properties, as we saw in the previous slides. And they can be used in combination with FBG sensors as point sensors, or with distributed sensing as well. So I hope with this session that I convinced you of the advantages of optical fiber sensors and how we would like to use them for asset monitoring, being the nervous system of that asset. Now, I want to also mention that we are active on different platforms that focus on innovation, help for photonics. If you want to include photonics in your company or in your product, have a look at these platforms, Photon Hub and Digitalis. They offer support not only on low TRL levels in orienteering and scouting and technology support better, but also financially and at different stages also on business coaching and investment coaching. And we even organize demo centers on how to use optical fiber sensors, etc. So certainly have a look. And if you think you want to use photonics to innovate in your company, or optical fiber sensors specifically, then don't hesitate to reach out. You can find my details here. Thank you very much for your attention.
Okay, thank you, Sydney, for your presentation. It's already 1 o'clock, but we still have some time for some questions. If there are people that still want to ask a question, you can just by raising your hand. I will give you the floor then. There is already one question in the Q&A. I will read it. It's from Nemo. Is it possible to distinguish wavelength shift due to temperature or due to strain?
That's a good question. So let me go to the slides that explain that more or less. And so with the FBG sensors, you induce a wavelength shift due to a strain or due to a temperature. Now the sensor is cross-sensitive to both. So you typically measure both strain and temperature at the same time. There are different ways to decouple between those. So typically, for example, if you measure very high vibrations in strain, you know your temperature is probably changing much slower than the strain you are measuring. So that's a post-processing way. Or you can include typically what one does is one installs the sensors for strain measuring to the structure while leaving one optical fiber sensor that is then also included in the same fiber, but it is not installed to the structure or not directly installed to the structure. So it sees the temperature of the structure, but it does not see the strain induced by the structure. And that can be done by including that one sensor into a capillary, for example, so that it is not influenced by the strain, but it is influenced by the temperature. But typically, to answer your question briefly, indeed, they are cross-sensitive to both strain and temperature. Now, these specialty optical fibers, there are ways to design these microstructures in such a way that you can distinguish between strain and temperature, but then we're not talking about standard optical fibers anymore. Then we are going a bit more advanced into these specialty optical fiber sensors.
Okay, thank you, Sydney. There is another question in the chat right now. If we can measure temperature, what accuracy are we talking about? Degrees, tenth of degrees, sorry.
Yeah, so that depends typically on the measurement device. So I'll go back to the FBG sensor here. So what happens if, so it's a completely physical analog phenomenon. So phenomenon. Difficult word today, apparently. So if we apply a temperature here, that temperature will change the properties, the physical properties of this grating, meaning that this peak will shift to the left or the right. Now, in your measurement device, you have a system not to go into too much detail, but you have a system that detects which color is being reflected and how that color changes to the left or the right. So it actually depends on how accurate your measurement system is and which increments of wavelength change you can measure with your measurement system. There are very high resolution systems that can go up to sub degree. Typically, the resolution that you can measure is 1 picometer, which is a tenth of a degree, I think. But you can go with higher resolutions. You can go lower than that. But usually they mention on the spec sheet half a degree is typically the accuracy that they mention. But a tenth of a degree is certainly possible. And like I said, by increasing the sensitivity of the measurement device, you could go even further than that.
Okay, thank you, Sydney. Are there other questions? If you raise your hand, I can also make sure you can use your mic and even your camera if you want.
If not, you can always reach out, of course, later as well.
Yeah, very good. Okay, then I think we can wrap up. So, Sydney, thank you again for your presentation. To the participants, thank you for being here. We will send you the recordings afterwards. And if you still have questions, please reach out to Sydney. Thank you.
Thank you very much, Dries.